Let's see, can you all hear me?
Yes.
Cool, and you can see my slides, perfect. All right, thank you for that introduction. My name is Sean. I'm a postdoc at UC San Diego. A postdoc is just a person who has recently finished their PhD and is now doing research full-time. So I do research full-time for my job, and hoping to one day be a professor. So that's the goal. I am a physicist, and I'm also an X-ray astronomer. And today I kind of want to give you all a sense of what that means, what it means to be an X-ray astronomer, as opposed to an optical astronomer or a radio astronomer, and the kinds of things that we study. And so, let's see. So here's a brief outline of what I'm going to talk about today. I want to start with a brief physics lesson and just talk about what are X-rays. And going to get a little bit fundamental. I just don't want to assume, any particular level of scientific training. So I want to make sure we're all on some base, sort of same page there. Then I'm going to talk about how are X-rays produced. What are the kind of physical phenomena that produce X-rays? Then we'll go to space and we'll see where are these physical phenomena happening out there in space. And then if we have time, which I'm not sure we will, but we'll see. If we have time, I'll talk about some of the specialized tools we use to observe X-rays from space. And so occasionally I'm going to get a little technical, and if not all of it makes sense, that's totally okay. Hopefully I'll make up for it with some pretty pictures, and hopefully we'll all learn a little something. So yeah, to start out, what are X-rays? So just like throwing you in the deep end here. So X-rays are light, but what is light? What does that even mean, right? So what I'm starting with here is just kind of a taste of how physicists started thinking about light, right? And so these equations on the left, and I don't expect folks to look at this and understand. It's totally fine. But what the equations on the left are called Maxwell's equations. And these are the equations the fundamental equations that describe electric and magnetic fields, right? And these are the fields that push and pull on particles with charge like electrons and protons, right? And so that's for studying things like current, right? Moving electrons. And so physicists understood how to, predict how current is going to move and how magnetic fields and electric fields affect current and those kinds of things. And what physicists found was that if you do math in a certain way on these equations, you get the form on the right. So these are basically the same equations, but written on the right. And for those eagle-eyed physics students out there who are currently taking E&M, maybe, you'll recognize that those equations, that kind of shape of equation is what we call the wave equation. So you can replace the individual E's and B's and the Greek letters in there. And that general shape just describes waves. So if you have waves in water, if you have waves in a slinky, you have sound waves, all of them are described by equations of that kind of shape, okay? So there's some hint here that electricity and magnetism can produce waves of some sort, right? There are waves in those fields. Oops, too far. And, from experiment, some of these numbers in the equations have been measured. So this mu and epsilon, those Greek letters that I've circled, these give the speed of the wave in the shape of the equation, and it happens that this matches the speed of light, right? So this is kind of crazy. Imagine you're here in the lab studying charges, electricity, and then you do some math, and the speed of light falls out of your equations, right? And it's a wave equation. So this sort of was the way that physicists determined that actually light is a wave in electricity and magnetism, right? And so, yeah, light is electromagnetic wave radiation. And so on the right, I'm showing sort of an illustration of what that wave looks like. And so here, the red is supposed to be the electric field going up and down in space and in time. And the blue is supposed to be the magnetic field, right? And so that's the basic picture of what light actually is. And then if you do more math, what you find is that to produce these waves, you accelerate charges. So So when physicists talk about acceleration, it's not just pushing on the gas. It's any change in how fast something's moving and also the direction. So acceleration is turning that steering wheel, it's pushing the gas, it's pushing the brakes. Any kind of like change in the motion is what produces light. Okay, and basically the faster that motion, right, the faster that acceleration, the shorter the wavelength, right? So this bacon symbol is supposed to be waves. And so you can imagine that like the faster my little electron on the left is moving, the more squished this wave is and the shorter the wavelength. And importantly, light doesn't just look like that like train of waves that we saw before. Instead, light bundles itself into photons. And photons are just these like packets of waves, like what I'm showing here, right? But you can see that it still has that fundamental wavelength, right? The distance between the like spikes is what we call the wavelength, and that corresponds directly to the energy. So the shorter the wavelength, the higher the energy, okay? All of this is just to say that all electromagnetic waves are light. So everything from radio waves down in the, low energy here. So what I'm showing is basically like a spectrum of light all the way from low energy, long wavelength with radio waves, all the way up to what we call gamma rays, which are the highest highest energy forms of light. And we have different names for these: radio waves, microwaves, visible light, right, which is kind of here in the middle here. But it's all the same thing, essentially, right? So X-rays are just light with a particular range of energies. And it's a higher energy than like visible light and ultraviolet light, right? So these are high energy X-rays, or high energy photons, basically. And if you're looking really closely at this kind of complicated image that I pulled from the internet, what it shows is this like gray kind of bulk. If you're seeing like the gray kind of like wiggly part, that's just showing at these different wavelengths how easily can this kind of light pass through Earth's atmosphere. And what we see is that like, okay, visible light passes through very easily. That's why we've evolved to see it. X-rays do not pass through. So that should be some foreshadowing in terms of where we have to put our tools in order to find X-rays. Okay, now let's talk about how X-rays are produced. X-rays are high energy light. Okay. And so because, oh yes, perfect. Awesome, thank you. So as you can imagine, these are photons, so it's high energy electromagnetic waves. And so X-rays come from regions of high energy, okay? And so one of those, so I'm gonna talk a little bit about like what are the processes that produce high energy photons. And one of the fundamental processes, or kind of like regions in space where we'd see this, is places where there are extreme temperatures. So, if you do some math and see what temperatures correspond to high energy photons or X-rays, you find that X-rays probe temperatures more than 1,000 times the surface of the sun. And this is, X-rays are emitted through a process called blackbody radiation. And blackbody radiation is essentially just the like latent radiation that anything that has a temperature gives off, right? So you and I are all giving off blackbody radiation. The sun is giving off blackbody radiation. The universe itself, in the form of a cosmic microwave background, is giving off blackbody radiation. And again, I'm showing some charts and math, and I apologize, but what I want to show is this sort of like kind of important concept of what we call a spectrum here. And a spectrum, when I talk about a spectrum as an astronomer, what I mean is really just like how bright is a thing if I plot the brightness as a function of wavelength or energy. So if I take bins in energy and put the photons in the bins, which bins have the most photons as a function of energy? And blackbody radiation, basically, you have some amount of brightness as a function of energy that changes depending on the temperature of your object. And so the hotter it is, the more energy your photons are going to have, basically. So again, X-rays probe temperatures more than 1,000 times the surface of the sun. So remember extreme temperatures. The next concept is accelerated particles. So again, as I mentioned before, light is produced by moving charges around, pushing charges around. And so you can imagine that energetic light, like X-rays, are produced by highly accelerated particles. So we're kind of looking for particle accelerators in space. And I mentioned before that electric and magnetic fields push and pull charges around. And so if you're seeing high energy events, then you're seeing very strong electric and magnetic fields. So those are another thing we're looking for, accelerated particles. The last thing I want to touch on before I get to the good pictures and stuff is radioactive decay. So, you know, folks are probably familiar with like the concept of radioactive decay, right? You know that a thing that is radioactive, you don't want to get near it because it's shooting things out of it, right? Essentially what radioactive decay is we have heavy atomic nuclei, so atomic nuclei that have a lot of neutrons and protons, these fundamental particles that make them up, and they're in unstable states. Essentially, they're in a state, some configuration, and they want to be in another configuration. And so eventually they'll move from this unstable state to a stable state. They'll move to the configuration where they feel most comfortable. And when they do that, they can emit radiation in different forms. Here, this picture is showing alpha decay, and so it's spitting out 2 protons and 2 neutrons, right? So it's literally just like, I don't want these 4 particles, I'm going to eject them. But there are different forms of radioactive decay, different channels essentially, and sometimes it spits out X-rays, right? So some places, sometimes we'll see X-rays as a sign of radioactive decay. And the reason I'm lumping this in with these like high energy events like extreme temperatures and highly accelerated particles is because radioactive decay, I want you to think of it as like, it's a tracer of past energetic phenomena, right? Essentially something in the past, violent and energetic, happened and locked energy away in these nuclei, and now they're sort of leaking that energy out over time, and we're seeing it in the form of X-rays. Okay, so fundamentally, X-rays let us probe energetic phenomena, right? More energetic than we would see using radio telescopes and that we would see using optical telescopes. And so what I'm showing here on the left is the view of our galaxy's disk, like if we're looking at the disk of our galaxy straight on, in all sorts of different wavelengths, right? All the way from like radio, microwave, visible somewhere in here, and then up to X-rays and gamma rays. And you can see like the shapes and the things, the features that you're seeing are different because we're probing fundamentally different physical properties. And sometimes these properties like happen in the same place, and that gives us hints that maybe there's something special happening in this region of space. Star formation, right, has many different physical phenomena happening. Another example I want to show is the Crab Nebula, which I'll talk a little bit more about later. But essentially, this is a composite image with many different, in many different wavelengths, from the radio all the way through the X-ray. So again, X-rays are letting us probe some of the most energetic phenomena in space. Okay, so where do these things happen? These extreme temperatures, accelerated particles, and radioactive decay. So oftentimes what I look at are the leftovers of stellar life cycles, right? One example is what we call supernova remnants. So a supernova, as folks might know, is when a star, it burns all of its fuel. Eventually, it's left with an iron core that it can't burn anymore, and then it collapses. It can't hold itself up, it collapses, and it explodes in a supernova. And we see the remnants of this in things like, again, the Crab Nebula I'm showing again because it's really cool. You know, when we look out in the night sky with something like Hubble, we see something like this, just kind of like a cloud of gas, like where the star exploded and just like spewed material everywhere. And when this happens, it crushes like atomic nuclei together, and it forms heavy nuclei, right? So alarm bells should be going off in your head. Heavy nuclei, some of them are unstable, right? And so here I'm showing the periodic table, and I want you to just focus on the yellow and the white. Those are the elements. You know, iron we have here. We have cobalt, nickel, all these metals, right? These are the elements that are produced in supernovae. And some fraction of these are going to be unstable, right? And so we'll see clouds of this radioactive decay happening in space where there was a supernova at one point. Again, this incredibly energetic event that has now like locked away energy and is letting us see it now. One thing I want to really quickly say about the Crab Nebula that I just like fell down a Wikipedia rabbit hole is that there's like, this was very close to Earth, or is very, very bright when it occurred. And we see like in historical records, particularly in China, where they were keeping very good historical records 1,000 years ago, that they saw this happen, but with their naked eye, right? Like they saw a new star in the sky that was like changing over time, changing color, changing brightness over time, so bright that you could see at night, like where you were walking at night. And now we're still doing science on this thing 1,000 years later. I think that's just like amazing. So we use X-rays to probe supernova remnants, like I said before. And so this is some work on the left by my friend Brian Greffenstedt, who is also at Caltech. He basically traced X-rays coming from this other supernova remnant, Cassiopeia A, and he could see signs of different elements, right? Again, looking at that radioactive decay, he saw signs of titanium in blue, signs of iron in red, signs of silicon and magnesium in green, right? And you can see they all have these different shapes, right? And so by using X-ray astronomy, we can actually map out how a supernova, like the shape that the supernova took, even though it was 1,000 years ago, we can start to map out how did all these things get kind of spewed out and what was the shape. And that starts to tell us about like the models of how supernovae actually are triggered and how they occur. Okay, the other thing we can do with supernovae remnants is not just looking at the radioactive decay, but we can kind of X-ray them. And so again, let's look at that Crab pulsar, but let's look at it just in X-rays. What we find is something totally different than what we saw with something like Hubble, right? We see this kind of like disk kind of gas going on here, some central object that's spewing a jet. And so what we found using X-rays is that there's actually a pulsar left over, right? So after this supernova occurred, it left behind what we call a neutron star. And I'll talk a little bit more about neutron stars later, but essentially they're like the core of the star collapses in on itself, and the material is crushed so dense that it's basically like the densest material we can see in our universe, right? The protons and electrons are squished together into neutrons. It's just a ball of neutrons that are so close to each other that they can't get closer any closer than they already are. It's held up by degeneracy pressure, which I'm not going to explain what that is, but like geometrically, they can't get any closer to each other. It's kind of like it's wild quantum mechanics stuff. So and so neutron stars are the densest material in the universe. They are fitting the mass of our sun or more, or 2 masses of our sun in a space the size of Los Angeles. Insane. And so this, by using X-rays, again, we've X-rayed this supernova remnant, we found one of these neutron stars, and we see that it's accelerating particles, and that's what we see. That's where this emission is coming from, is that this pulsar has really strong magnetic fields, and it's accelerating particles outwards in these jets and these shocks. Okay, the other place where we can see the leftovers of stellar life cycles are black holes. This is not a real picture. I think this is from Interstellar. How many have seen Interstellar? Yeah, pretty good movie. Matthew McConaughey. Yeah, so a black hole is kind of like a neutron star in that it's also like a remnant of, after a supernova, the core of the star collapses. And in this case, there's so much mass that it can't even, not even neutron degeneracy pressure can hold it up, right? Not even quantum mechanics can hold this thing up. Now it's just a hole in space. I'm saying this kind of like to be funny, but also it's kind of true that it's like the universe just doesn't know what to do with this region mathematically, so we're just going to say it's not there. Okay, there's a hole there now. And so you might think, okay, wait, how can we see those, right? Like black holes, nothing's supposed to escape, light's not supposed to escape. That's true. But we can see black holes when they interact with material around them. And so the kinds of black holes that I usually look at are those that are in a binary system with a regular star, a star that might be like our sun or it might be a supergiant star. But the kinds of stars that you think about when you look out in the night sky, it's in a binary system, so it's orbiting around they're orbiting around each other, kind of dancing around each other. And if they're close enough together, material will actually get pulled off from the gravitational field of the black hole, pulled off the surface of the star, and start to spiral into the black hole. It'll start to fall towards the black hole. And as it does this, it's kind of like spiraling in the drain of your sink or your bathtub, except that it's like way hotter than that. It's 10 to the 7 Kelvin, so like 10 million degrees. This is where those extreme temperatures I was talking about earlier were. So that gravitational potential energy, for the physicists out there, is being transformed into thermal energy. This is one of the most, maybe the most efficient kind of like transformation of energy process in the universe, where we're taking the energy, the gravitational potential energy, which is essentially like the energy it takes to be able to fall, right? That energy is being turned into heat. And again, at the very innermost regions, when we get closest to the black hole, we're seeing temperatures thousands of times the temperature of the sun. And we see accelerated particles yet again. I've heard people describe black holes as messy eaters, right? So as material's falling in, things are getting really hot, really bright, and material can sometimes be ejected out in these jets, right? And so we're seeing that acceleration of particles, and that way those particle accelerators in space. Okay, and here's what a black hole looks like in X-rays. A little less exciting, but this is actually the first black hole that we ever confirmed, that astronomers ever confirmed. This is Cygnus X1. It's one of the brightest X-ray sources in the sky. If you look out with an X-ray telescope, this is one of the brightest things you'll see. This was intriguing to astronomers, of course, when we first started sending X-ray telescopes into space. We saw this crazy bright thing. And basically by looking at its spectra, both in the X-rays and in like optical and radio, by looking at the spectra, which again is the brightness as a function of energy, like how bright a thing is if you slice it up in energy of photons. By looking at the spectra and how they change, it is determined that the only way we can describe this thing is if it's a black hole eating up material from a star nearby. Another really cool thing we can do with black holes in the X-ray in particular that we really can't do at any other energy is what's called reflection spectroscopy. This starts to get a little technical, so I won't get into super detail, but the idea is basically that we have these accelerated particles, right? That's producing light above this disk. We have this accretion disk, the spiraling in material, right? Those accelerated particles are also producing light. That light, some of it, shines on the disk. You've got kind of this like lamppost that shines on the disk, and then the disk like re-radiates like a mirror or something, right? It reflects that light back at us. And because in the regions closest to the black hole, there's crazy physics going on. So again, if you've seen Interstellar, you'll recall that when they're on the planet near the black hole, time is moving more slowly. We're seeing that. We're directly measuring that happen, right? And that's what's called redshift and blue shift here. So again, I don't expect folks to look at this and be like, oh yes, I understand. But the idea is that we can physically model that kind of time dilation at different parts of the disk. And then we can transform that into, well, what do we expect to see in the spectrum then when we point a telescope at it? And then we can do some math and understand things like how fast the black hole is spinning. Black hole spin, kind of weird. We can understand, how the shape of this disk, how far in does the disk go before the material just kind of falls right in, that kind of thing. So, and truly, really, we're doing all this physics with basically these data points. And some extra ones up here that I'm not showing. But I don't know. It's mind-blowing to me. This is my work of it. That's fine. How am I doing on time? Okay, cool. So I mentioned neutron stars before. And so in addition to those pulsars that we see that are kind of isolated, in the Crab Nebula, so that's kind of a neutron star by itself, spewing material. Here, we have I'm talking about neutron stars that are in that kind of binary system, just like the black holes I've talked about. So these are called X-ray binaries, and they can be black holes, neutron stars, even white dwarfs, which are another kind of thing. We call these things compact objects. So a neutron, if I say compact object, I mean a black hole or a neutron star. And so oftentimes when we look out with our X-ray telescopes, I mean, again, remember we saw that blob, right? No one can look at that blob and immediately, just from looking at the blob, tell you that's a black hole. And so in a lot of cases, we can't tell immediately, are we looking at a neutron star or a black hole? Because this accretion process is happening in both of them, this material falling in, spiraling, creating a disk, because this is happening in both cases, often they behave very similarly, right? But kind of a fundamental difference is that neutron stars have these, magnetic fields that are kind of similar to, they're not really similar to like the Earth's magnetic field, but kind of like you can imagine, right? Like kind of like a pole, like North Pole, South Pole, but they're very strong, right? So it has those strong magnetic fields, and it also has a surface. A black hole doesn't have a surface. Once material reaches the black hole, it'll just fall in. Whereas on a neutron star, stuff can like pile up on the surface of the neutron star, right? And then you get all sorts of weird effects. And so here I just like made a little drawing. This is from my thesis presentation. And I was very proud of this drawing, so I'm going to use it in every presentation until but basically what I'm showing here is the disk kind of coming in. So if we're like looking at a cross section, right? The disk of spiraling material falling towards it. In a black hole, eventually it reaches what we call the innermost stable circular orbit. Essentially, in a black hole, it gets close enough and then falls in. With a neutron star, sometimes the magnetic fields are strong enough. Again, magnetic fields push and pull charges, right? Like I said, electric and magnetic fields push and pull charges around. And so if the magnetic fields are strong enough, they can actually pick up the charged particles from the disk, they disrupt the disk, and the material, rather than just kind of going all the way to the star, the material falls on the poles, on the magnetic poles, right? So you have all this really hot material, again, like thousands of times the temperature of the sun, right? All this hot material falling on the magnetic poles of the neutron star, and it creates like a lighthouse effect. So as this pole, if we're looking at it from far away, this hot spot, right, which I'm showing in orange, will come in and out of our line of sight, just like a lighthouse, right? And it produces a pulsar, a thing that looks like it's like really bright, really dim, really bright, really dim. And these on the right are showing what we call pulse profiles. So essentially just showing that change in brightness where, on a very regular time scale, based on how fast the thing is spinning, it gets bright, it gets dim, it gets bright, it gets dim, right? So that's something when we see that, we're like, okay, that's for sure a neutron star and not a black hole. The other thing we can see, again, some charts, is because it has a surface, in other cases, material piles up on the surface, and eventually you get thermonuclear explosions on the surface of the star, in some cases, depending on how fast material is building up. So again, this is something you don't see in black holes because the material just falls right in, and it's gone forever. Here, the stuff can build up and build up and pile up, and then eventually it gets to a critical density, and the entire surface of the star burns all at once, and all you're left with is ashes, and then the cycle starts over. And so the way these are called type 1 X-ray bursts, and the way that we identify these is if we look at the brightness as a function of time. Again, here is like how many photons we're seeing as a function of time. You'll see most of the time it's just kind of bubbling along, but every once in a while we get these giant spikes where it gets like hundreds of times brighter than it usually is in sort of like persistent state, right? And it only lasts like briefly, so like tens, hundreds of seconds. And that's what's called a type 1 X-ray burst. So the entire surface is covered in thermonuclear burning, and then it stops, leaves the ashes, and starts over again. And we can learn things about what is the material that's falling in, right? How fast is the material piling up? Those kinds of things. That's fun. The last sort of like physical phenomenon that I want to talk about are supermassive black holes. So I talked about black holes generally. Well, I talked about like stellar mass black holes. So black holes that are close to the mass of our sun. Again, they're in orbit with a regular star. So they're around that kind of like size. Whereas supermassive black holes are billions, tens of billions of solar masses, right? These things are enormous, like to the point where we don't really understand how they got this big in the amount of time that the universe has been around. People are still trying to figure that out. On the left here, I'm showing one of the best images we have of a black hole from the Event Horizon Telescope. A lot of folks may have seen this image already. If not, I encourage you to read more about it. This is using radio waves, not X-rays, but it's a cool picture. On the right here is kind of our physical picture of what's happening around a supermassive black hole at the center of a galaxy. And so we call them active galactic nuclei when they're in the center of a galaxy and they're accreting material and shining really, really brightly. And so again, that accretion process shows up. We see an accretion disk around the black hole, just like we did with the black holes and the neutron stars I talked about before. This material isn't coming from a companion star or something. It's just the stuff around it. There's stuff around it and it becomes a disk and spirals inwards. In addition, again, this is at the center of a galaxy, so there's a lot of things going on around here. We've got these clouds nearby that are really, really hot and really bright. We have this jet that can be launched out. Again, that's our accelerating particles, and we've got our extreme temperatures. And then also we see this dusty kind of donut around it, kind of hiding it from view, depending on what angle you're looking at it from. So the takeaway here is really, depending on what angle this thing is oriented at, you're going to see a totally different picture. But if we're looking at it in this way, down at the disk, then we're seeing lots and lots of X-rays from this thing. We can do cool physics. And so here I'm just showing some pictures of that same black hole, Messier 87, using all different wavelengths. And so again, we're going from lower energy photons, radio waves, up through visible here with Hubble, all the way up through X-rays. So these are X-ray images of that active galactic nucleus, all the way up to gamma rays. So gamma rays have even more energy than X-rays. And again, I think the takeaway here is that we use all these different wavelengths, right, to see different things happen. We see these accelerated particles. We see the extreme temperatures, right, with the X-rays. Radio helps us see accelerated particles that are accelerated in different processes, and so on and so forth. So we need all these different kinds of instruments to see all different kinds of physical processes and learn and kind of form one whole picture about what's happening with active galactic nuclei, these supermassive black holes that are so mysterious. Another really cool thing about supermassive black holes is they sometimes produce tidal disruption events. And a tidal disruption event, this is a simulation, by the way, not a real picture, unfortunately, but hopefully gives you an idea of what's going on. So a tidal disruption event is, imagine there's a supermassive black hole here, right? Again, we can't see it because it's a black hole, but we can see that something strange is happening to the things around it. And this line is actually a star. So a tidal disruption event is when a star comes close enough to a supermassive black hole that the tides themselves rip the star apart and material from the star forms that accretion disk again, and it lights up those extreme temperatures, those accelerated particles, and creates X-rays. And so this is the same kind of it's the same tides that make our tides, right? The same tidal forces that kind of stretch out the ocean and stuff on the Earth due to the moon. This is like that to the extreme, where this supermassive black hole is just ripping the star apart and material is falling in. And so we see that in X-rays, right? And again, this is an instance where we didn't see this picture, right? We saw something happening in the X-rays, and we had to think about, how do we describe what we're seeing? The way this event is changing over time, the way the spectrum, again, the energy distribution of the photons looks, all of that, how do we describe this? And came up with this picture. So in the last few minutes, I'm going to kind of speed through this, I think. But I want to talk about a little bit, what are the tools that X-ray astronomers use? How do we come with those pictures that I showed you, right? So X-rays have a tendency to pass through things. That's kind of like their whole deal, right? We go to the dentist and we want to see our teeth, and we want to see our bones and not all the other bits. So that's why we use X-rays, right? But again, they don't pass through our atmosphere, right? Our atmosphere is thick, and there's lots of oxygen and nitrogen, and there's lots of opportunity for X-rays to get absorbed. And so we have to go to space. So we send telescopes into space to look for X-rays from space. And so we need specialized tools to collect these X-rays. Again, because X-rays want to pass through things, we need to use materials that are dense, essentially. So materials that have a lot of like protons and neutrons, a lot like big atomic nuclei. So there's lots of opportunity for an X-ray to come in and interact, and we can learn about it, right? We want to stop the X-ray. We want to stop the X-ray and say, how much energy do you have? When did you get here? Where did you get here? Like all this stuff. And so we need large atomic nuclei to do that. I don't love this slide. I feel like this doesn't tell you what I just said, but that's okay. So this is an example of the kinds of detectors we'll use. Again, kind of nitty-gritty, but just to give you the idea is that we use crystals. We basically use crystals to measure X-rays. Or at least the detectors that I work with are semiconductor crystals. So, we have a block of something like germanium, something like cadmium, zinc, telluride, these atomic nuclei that have a lot of protons and neutrons. And then we take one of these crystals, which takes a lot of time and effort to grow the crystal in the first place, but once we have it, we stick some electronics on it, and the electronics are kind of watching the crystal and saying, okay, I saw that a photon came in and bounced off this crystal, or like was absorbed into the crystal, and I know how much energy the thing had, and I know when it came in and all this. Because again, ultimately that's what we want, is to measure those individual photons and learn about them and look at them as an ensemble and figure out what the heck we're looking at. In addition to like specialized detectors, we need specialized mirrors as well. Again, X-rays want to pass through things, and so the way we usually want to make an image, right, with a regular, like a telescope that you might be familiar with, something like Hubble, or even the telescope you might have in your backyard, we use lenses and mirrors that we're familiar with to bounce the light around and make an image, to focus an image. But X-rays, again, want to pass through that mirror. But what we find is that actually we can focus those X-rays, but the angle of reflection has to be really, really narrow, right? It's like skipping rocks against the water, basically, is what we have to do. And so we have to build very specialized mirrors, these parabolic mirrors, right? Grazing incidence optics, as they're called. And so that these X-rays come in and they bounce, and they really are only deflected a little bit onto our image plane, right? And so it requires these long focal lengths, and in other words, like a long distance between the mirror and the detector, so that we can do that really small bounce. And we have to use mirrors that are different materials, like piled on top of each other, to measure different energies. Okay. And so we can use some combination of all these different like strengths and weaknesses to create different instruments, depending on what other things we want to study. I'm just going to highlight three main observatories that are important for X-ray astronomers. There's a lot of them. The first is the Chandra X-ray Observatory. So this is one of NASA's great observatories. That means it's one of the most important instruments that we have for not just for X-ray astronomers, but just the astronomical community in general. It's incredibly powerful. These are some of its strengths that I've put over here, or just sort of some of the tech specs. It produces really sharp images compared to a lot of other X-ray telescopes. And so, some of those jets I showed you in the X-ray, Chandra is able to see those. It has good energy resolution. It can tell the difference between photons of different energy quite well. And this one happens to look at what we call soft X-rays. So X-rays that are kind of on the lower end of the X-ray spectrum. So, we saw that big spectrum of photons with different energy. Even in the X-rays, we kind of split it up into soft, low energy, and hard, higher energy. Okay? So again, here's some images produced by Chandra. Again, you get these beautiful images with sharp quality to them. NuSTAR is the instrument that I'm most familiar with. I did my PhD in the NuSTAR group at Caltech. Again, this is where I got those pictures of those grazing incidence optics and those semiconductor detectors. It has a really long focal length because it's going up to even higher energies. So essentially, that grazing incidence, we're skipping those rocks really, really low. And so we need an even longer focal length. And this thing expanded in space. And I wasn't around when that happened, but I've heard from my PI at the time that was extremely nerve-wracking. But NuSTAR is amazing, near and dear to my heart. It has really good time resolution, which helps to look at pulsars, again, where we're looking at for those blips. It has good energy resolution. And this looks at hard X-rays. So this looks at a higher energy range than Chandra and a lot of other X-ray observatories. So oftentimes we'll pair them together and be like, let's look at that star with both Chandra and NuSTAR at the same time so we can get the full spectrum of what's going on. And NuSTAR is really what made possible that reflection spectroscopy studies that I mentioned before. You can use other instruments to do it, but NuSTAR made it even more powerful. Okay, yeah, so that's what I'm showing here, is you can do that reflection stuff with NuSTAR. The last one I want to mention really quick before we go to questions is NICER, which is the Neutron Star Interior Composition Explorer. This is a box on the International Space Station. So you'll notice that it doesn't have that like long focal length. It doesn't look like the telescope that you're used to seeing, right? That's because this really is something like 56 buckets for collecting X-rays from space. So it doesn't produce images. It doesn't produce pictures even. We just look at a square on the sky with NICER, and because we have so much what we call collecting area, right, we can, in a short period of time, get lots and lots and lots of X-rays and learn something quickly, right? And especially that's useful when we're looking at events that don't last very long, right? Or when we're looking at pulsars, again, where that pulsation might only last, milliseconds. And so we need a tool that can get tons of photons. It has really good time resolution. Again, it's made to look at pulsars, essentially. Good energy resolution. It's in that soft X-ray band. And the reason it's called the Neutron Star Composition Explorer is because, again, it was made to look at pulsars and get that pulse profile exactly right. And there's been some incredible physics done with the data collected by NICER, where they've actually mapped out those hotspots that I mentioned, right, where the electric field or the magnetic field is creating these regions of high temperature on the star. And our kind of like our intuitive view before we got these results back was, well, they're probably kind of like a magnet, right? North pole, south pole. Maybe shift it around a little bit. But when you do the math, when you take what NICER found and do the math, you find these these magnetic fields that look totally weird. Like the pole has this crescent shape on one side, and the other side is this dot. And yeah, it's just like, this was totally unexpected and really incredible science. So that's what I've got today. I'm happy to answer some questions to the best of my ability here.
Neutron stars. I've seen references on the internet of very large neutron stars having the possibility that the cores are being held up by quark degeneracy. Any thoughts on quark degeneracy?
I don't have a lot of thoughts on quark degeneracy. That's just because I don't know that much about it. But astrophysicists, we don't have access to the inside of the star, right? We're looking at the surface of the star and the way that it's interacting with its surroundings. And so we're trying to use X-rays, observations, the ones I've explained, to essentially interpolate what's going on inside, right? And so, it might be that there's this quark model, right? That's one of the models of how a neutron star is held up, what it's composed of inside. And when you, again, do the math through the simulations, you find that that produces a specific relationship between the mass of the star and its radius, right? Those are two things we can start to get a handle on, is the mass and the radius. Again, we can't see inside, but we can start to get a handle on the mass and the radius. And so by measuring those things, we can start to narrow down, is it quark degeneracy? Is it something totally different?
Since you know the math, you talk about it a lot, where do you think things go when they fall to the black hole?
Ooh. Unfortunately, my answer is kind of it doesn't matter. We can't see it, and we'll never see it, and there's no way to know. Literally, that information is gone, right? I think that's even crazier, honestly, to think about, is that information is straight up gone. I guess technically, maybe it's holographically, on the surface of the black hole in some way. I think that's the understanding right now. But essentially, it's inaccessible to us. And so, could be anything. Yeah.
your center of every galaxy, does it have something to do with holding it together? I didn't understand the question. I hope you did.
Yeah. So not every galaxy has a black hole at the center of it. It's a good question. But the many galaxies do, right? But there are galaxies that are just kind of a large kind of blob of stars and stuff. Yeah. But yeah, there is an important interplay between the central black hole. So again, as I said, not every galaxy has a black hole, so it's not necessary to have a black hole to like.
The ones that have black holes have a different shape.
Yeah, so the ones that we see that have that like active galactic nucleus tend to be like spiral galaxies, like the kind of like disky region, but not all of them. Yeah. But yeah, there's an important interplay, right? So like I said, there's material falling into this thing, and like I said, they're messy eaters, so they're like spewing material out as well. And that, that's a kind of like an important area of study is how does that like feedback influence the way the galaxy evolves? And then how the galaxy evolves and impacts the black hole, right? So there's this kind of feedback loop of like the thing collecting material, shooting material back out, shaping the galaxy in that way, and then the way that it continues to evolve. I'm not like an AGN astronomer, so this is like my best understanding. Yeah.
When you're describing a new star, you reference skipping rocks. Can you describe what that concept is when you're comparing skipping rocks?
Yeah. So let me see if I can, yeah, something like this. So essentially when I'm taking myself back to physics class. Okay, so like we imagine this electromagnetic wave, that's our photon, right? Coming up against a reflective surface, right? Like a metal, right? Metals are reflective. The reason they're reflective is because the charges move pretty freely, right? Okay. Anyway, so when you do that, when you look at that, you can calculate when the wave hits the material at any given angle. You can calculate what's the probability that wave's going to just pass right through, and what's the probability, or what's the amplitude of that, the like part of that wave that will pass through, and the part of that wave that will reflect. And it turns out that as you go to higher and higher energies, you need lower and lower angles, right? So if we imagine, here's my mirror, right? And here's my light wave coming in. At the higher energy this light wave has, the shorter the wavelength, right? What am I trying to say? It's less likely to reflect unless you're at these really low angles, right? And so that's what I mean by like, it's like skipping rocks against the water, right? If we just throw it directly, if this photon comes directly in, it's most likely going to just, all of it's going to pass through, and most of it's going to pass through. Whereas if we have, this grazing angle, most of that energy will reflect.
Yeah, so to follow up on that, so is that the desired outcome so that gold rods will pick up the energy, the charge difference?
Yeah, so we know that's, if we want to bounce the X-rays in order to create images, we have to make mirrors that have this geometry. Yeah, and so yeah, exactly. We want those X-rays to bounce off the mirror and into our detector, right? Yeah, so we build it in such a way that we know the maximum number of photons will be funneled into the detector, and then when it hits the detector, that's where we again say, okay, now we can get a hold of this X-ray. We can stop this X-ray in its tracks and learn everything about it. Right? Yeah. Back there.
How frequently are you getting the X-ray data from different sources?
So there's a few different ways to answer this, I think. So we're always collecting X-ray data. So there's different ways that different telescopes work, right? So there are what we call all-sky surveys. So the MAXI, the Monitor of All-Sky X-ray Imager, is a Japanese experiment that's also on the International Space Station. That's always looking at the entire sky and scanning over the entire sky every single day, right? And that's always sending down data. And basically the idea there is, this thing, maybe you're not going to do all your really detailed science with this instrument, but it's keeping us aware of what's going on. So we can say, oh, something just went off in this area of the sky, let's go look at it, right? So that's that's actually like one of my projects is like using MAXI to say something's happening and then make NuStar look at it, right? And then, yeah, things like NuStar, they're pointing telescopes, right? So you really have to tell it, look at this part of the sky. It's not scanning. It's like you tell it what to look at specifically. And those telescopes are also always looking at something because scientists, like, why wouldn't you? Like, right? There's a big enough community that we're making sure to use all of that time to look at something, right? And so, there's always data being sent down. But different objects are bright at different times, sort of. So like some objects are bright all the time. Some things become bright for a few months and then fizzle out, right? And then maybe get bright again later. But there's always something happening. Yeah. Back there. Yeah.
So I want to step back a little bit because can you jump to that image of the crab nebula that you had, the purple one?
Where are we at?
There you go.
Yeah.
So, I mean, I'm following everything you're saying, but I just get to come back a little bit because, like, that's an amazing image. And the X-rays are something we can't see with our own eyes, unless it's being photographed on like a film somewhere. But I don't think you're on a film. So I keep thinking, like, how did you arrive at a physical picture that we can look at?
Yeah.
That from data or numbers that might help me a little bit.
Yeah. Okay, so this is from Chandra. And Chandra basically has like silicon detectors, right? So big silicon crystal attached to electronics, right? So that's our like film in this case, right? So that's kind of like our X-ray film, but it's digital, like it's like there's pixels, right? So it's like your phone camera but for X-rays in a sense. And basically, you have your X-rays coming in, and you can think of it like each pixel is telling you how many X-rays it's seen, right? So, pixel, one pixel here says I saw 100 X-rays. Pixel here says I saw 90 X-rays, so on and so forth. And then, we know things about like the energy of the X-rays and stuff like that as well. But in terms of like just making an image, basically we're saying at each pixel, to translate for us, for like you're saying, translating it for our eyes is just say the more photons that came in at a given pixel, make it more purple, make it more bright, right?
So
Does that make sense?
Whiter is on that image, for example, would have more pixels being excited.
Yes, exactly. Yeah. So whiter is like more X-rays. Yeah, and then darker is fewer X-rays. Exactly. Yeah. So yeah, it's kind of like it's similar to like a phone camera, but no.
No, that helps put it together a little bit, especially for us.
Sure. Yeah.
How do you guys share the access for the X-ray?
Sorry, what was the question?
How do you share the access for the X-ray?
How do we like is the data accessible? Is that what you're saying? Yeah, so all of the data is eventually publicly accessible, right? Sometimes there's a period when the person who requested the data gets it for like 6 months or something, so that they have time to like write the paper or whatever without someone coming in and being like, I didn't do the work to propose this, but let me take this data and write about it, and then now your thesis is kind of messed up, right? So sometimes there's this kind of proprietary period. Eventually all the data comes down. And the way the data looks is basically like a list of numbers. Like you basically get like big files that are lists of numbers, lists of like each photon, when did it arrive, each photon, what was the energy, for example, for like something like NuStar that I'm familiar with, right? And then there are specialized tools to like analyze it. So to like take this, sort them into like spectra, or like start to understand pulsations, like when relationships between the times that photons arrive and things like that.
But if you learn it, let's say, if you want to find out about any stars, maybe you utilize the access to the X-ray or
Right. So if the data has already been, like if the star has been observed, that data is most likely public online. and so you go into a database and you say, I want to see this patch of the sky, or I want to see this object with this name, or something like that. If you want to make a new observation, often depending on the telescope, but again, there's only so much time to look at things. And so you have to, like, you apply for time, basically. So you write a proposal and you say, here's the thing I want to look at, or like the kind of thing I want to look at. Here's why, here's the science I expect to get out of it. And specifically, you have to argue like the efficiency of the use of the time, basically. And then, a group of your peers come together and they look at all these proposals and they say, yeah, this looks like a really good use for this telescope in this amount of time. Let's do this. Let's look at that thing. Let's do the plan that this person said. Peer review. Yeah, exactly. Yeah.
You showed a neutron star, the magnetic field tearing the accretion disk apart.
Yes.
Pulling it onto the poles. And then there was another one, sort of a follow-up, yeah, this one, where it treats out material and you get this permanent glass.
Yeah.
Little pulse. On a white dwarf, you pile up material like this and you get a nova or a supernova.
Right.
Why does something like a neutron star, which is going to be pulling in a lot more energy, pulling this stuff in, produce kind of a blip and a white dwarf blow itself apart?
Yeah. So, yeah, essentially what you're talking about is like type 1A supernova, right? Is when a sort of analogous process happens where a white dwarf, which is also a remnant of the star, like builds up material and eventually explodes. And so my understanding of the difference here is that a white dwarf, like the stuff that the white dwarf itself is made of, is burnable, right? And so you have the explosion on the surface just like this, but it can, if it has enough energy, it can kind of like penetrate into the star and ignite the star itself. Whereas here, that's not happening, right? This stuff is not like burnable in that way. It can't, yeah, it's already burned. It can't undergo thermonuclear burning in the same way. So that's why. Yeah, good question. Yeah. Yep.
Well, the physics of the ejection jets on black holes understood. You always see these diagrams, and the accretion disk is sucking in that. And then totally away from that, you're seeing jets flying out.
Yeah.
Does that data? Does the matter go into the black hole and then it's kicking out of the matter somehow? Or is this like being bounced off?
Yeah, so it's the specific process that produces these jets, to my knowledge, is not fully understood, right? It's, but it's not like it goes into the black hole and then the black hole spits it out, right? It is like material from the disk that is being essentially ejected, like before it has a chance to fall into the black hole. One of the ideas is that you've got all this material kind of like flying around, and you have like the sort of like remnant magnetic fields from when the star exploded, and so there's like these really tangled up magnetic fields, and that geometry can essentially accelerate particles out. So that's one way that you can get outflows from a black hole, is like strong, complicated, tangled up like magnetic fields that produce these jets. Another way you can get outflows is the disk itself. If the disk itself is bright enough, like the light from the disk will actually like push material off the surface of the disk and produce like winds and outflows and stuff like that. Yeah, but yeah, that's less of like a jet geometry than like a wind. Like a, yeah. Yeah. Maybe that too.
The magnetic field can't penetrate into the black hole.
Right.
All the magnetic fields have to remain outside.
Exactly. Yeah. So that's like threading the like inner regions of the disk and stuff like that. Yeah. And then you got space is spinning around, and the disk is spinning around, and it's like complicated things. So how do we feel about one more question? Two more questions. Okay, Ethan, and then you and the group. Yeah, Ethan, go ahead.
So back to that slide on the jets and like the magnetic field sucking in those particles. Is that sort of like a model for every neutron star? Like, is that something we're confident is like that's the source of the jets on like all neutron stars?
So you're talking about this picture, right? So this is not. Yeah, I think my illustration is maybe a little misleading, especially because I was jumping from like jets to this. This is not, these are not necessarily meant to evoke jets. This is like the light coming out of the hotspot. And we don't expect to see this picture in every neutron star, right? So the jet that I was showing with the Crab Nebula, it doesn't have the same kind of like accretion onto like the magnetic poles and all of that stuff, right? It's like there's charged particles kind of floating around it, and its strong magnetic fields are like accelerating jets like that. Accreting neutron stars like this one, we sometimes have this picture where the magnetic field picks up material and puts it on the poles. But if the magnetic field isn't strong enough, right, there are sources that we see where the magnetic field isn't strong enough, where the material just comes straight to the surface. And that's actually where we see this kind of behavior, is when the magnetic field is not threading, like not picking up the material, it's just like going straight to the surface. The material is going straight to the surface and kind of like spreading over the neutron star. And that's because they have weaker magnetic fields. And I think there was one more question. Yeah.
What is the closest black hole to Earth?
I don't remember. Sorry. Yeah, I don't remember the answer to that question. I did look it up before this, but I forgot the answer. Yeah. That's a good place to end with I don't know. Yeah. Thanks, y'all.
All right, thank you everyone for coming out here. We'll have our telescopes out at the telescope farm if you want to take a look at Saturn or perhaps some double stars.